Let's do an example. Produce a dy dx vector at 1, 0 and 1, 1 for the system. Dx dt equals x plus 2y and dy dt equals negative x minus y. Okay, so at the point 1, 0, we're going to have two vectors. So here's 1, 0, and at the point 1, 0, we need to generate a dx dt and a dy dt. So we're going to generate both these slopes. To get the dx dt, I have to take 2x plus y. That was our differential, or sorry, x plus 2y. So the x value is 1. 2 times the y value, that's 0. That gives me an output of 1. To calculate dy dt for the point 1, 0, that's going to be negative y minus x, or negative x minus y. So that's negative 1 minus 0, and that comes out to negative 1. Okay, so at this point, I'm going to plot two vectors. So dx dt tells me that in 1 unit of time, I expect x to increase by 1. So let's go ahead and do that. So there's my dx dt, and that means in 1 unit of time, I expect x to change in one unit. This is because x is positive. Earlier we were trying to make the observation that dx dt could be positive, negative, or it could also be 0. So in this case, dx dt is positive, which means in 1 unit of time, I expect x to increase. Okay, so x is going to increase by 1. So this is my representation of dx dt equals 1. Dy dt is negative 1, and that means I expect y to decrease by 1. Okay, well, the y-axis is this axis here. The x-axis is this axis here. So to have y decrease by 1, that means y is going to go down this way. Now this is again in 1 unit of time. So in 1 unit of time, if x moves to 2 and y moves to negative 1, then the result, or the resultant vector, is that we will end up at this point here, right? So x will increase by 1, then y will decrease by 1, and we'll expect our vector to point down here. So this blue vector is dy dx. That's the change in y per change in x. So the slope of this line is really negative 1 to 1. Negative 1 rise to a positive 1 run. And the problem wants us to also repeat this for the point 1, 1, which is this point here. And I'm going to do exactly the same thing. I'm going to calculate the dx dt at that point. Dx dt is going to be x plus 2y, which is 1 plus 2 times 1, which is 3. And the dy dt at that point is going to be negative x minus y, which is going to be 0. I'm sorry, not 0, negative 2. So that will be negative 2. And so once again, what I'll do is I'll plot two vectors. And one of those vectors is going to, well, my x vector is saying that x is supposed to increase by 3 in 1 unit of time. So to increase by 3, well, that means we'll go from 1 all the way over here to 4. Sorry, that doesn't look real great. That's dx dt is going to increase by 3. My dy dt is going to decrease by 2. So actually that would put me at the same point down here. And that's dy dt equals negative 2. And so as a result, my resultant vector is going to point, well, if x goes from 1 to 4, but y goes from 1 down to negative 1, that means my resultant vector is going to point right there. And that's my dy dx is y going to decrease by 2 as x increases by 3. So the slope of that line is negative 2/3. Now this is going to be very tedious because we have to do this, generate two vectors, create the resultant vector for all of these points. And also notice that that this vector here is longer than this vector here. So you can probably imagine that some of these vectors are going to start to intersect one another. The green and the pinkish vectors are not ones that we actually want on there. Those just assisted us in helping the blue vector, which describes in 1 unit of time what's going to happen to those two populations. So what we'll do is we'll shrink these down proportionally so that this longer one will still be longer even after we shrink it down. So maybe we'll take like 1/10 of it and we'll shrink it down. We'll take 1/10 of this and shrink it down and repeat this for many, 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 many points. We get something that looks like this. And you can see that right around the point 1, 1, which is right about here, we see that there are vectors that point right and down. And that was because dx dt was positive and dy dt was negative. The vectors should point to the right and down. If we had done this over here in the fourth quadrant, you see that these vectors, like this guy here, points to the left and a little bit up. That would mean that dx dt, well, x is decreasing, because this is the x-axis, and that means that y is increasing because the vector points upwards, and this is the y-axis. So I probably should be careful about my labeling here, but this is the x-axis and this is the vertical y-axis here. So if we generate this for many points, you can see what's happening here, that there's sort of this flow, and x and y seem to be sort of flowing into these elliptical shapes as time passes. And again, this is just repeating our process up here for many, 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 many points. This little applet, if you go over to the site, will allow you to generate this slope field. Let me just show you. So here's what this looks like, and you can see it allows you to enter x prime, which is the same thing as saying dx dt. So I had to do x plus 2, and then a multiplication sign is necessary, times y, and then negative x minus y, and then I just set my display here. So you can see that, you know, some of the arrows are a little bit longer because in 1 unit time, in some locations, you're going to have bigger changes in both x and y than in others. You can see this guy is a little bit shorter than, say, this guy over here is a tiny bit longer. And so that's just because these represent what's happening in 1 unit of time. So actually I can click on this plot, and what this does is it just generates using a numerical method, kind of like Euler's method, similar to that. It just generates a lot of points and then connects them. And you can see, depending on what initial condition I pick, the oval just changes shape. So x and y seem to be cycling over and over and over again in this elliptical fashion. So I can remove those and I can just look at one. And you can probably kind of sketch that out in your head what that would look like. So if I picked 1, 1, you can kind of see that would be an elliptical mode. But if I click on around 1, 1, it'll generate the full-on curve. So it's kind of hard to see just by the vectors, but you can at least see the flow of how x and y are going to change over time. So let's say that what we wanted to do is we wanted to sketch what x and y would do over time. That is, again, keep in mind that time is not in this graph. The only representation of time that we have here is how long these vectors are, because each of these vectors, once again, represents what happens in 1 unit of time. So even though we can't necessarily solve this equation, we can kind of see what's happening to x over time. The time axis we're not really going to label because we don't have any sense of time in this graph, but I started off with the point. My initial condition was the point 1, 1. That's what we wanted in the problem description up here. Sketch a y versus t graph and an x versus t graph by using the phase plane above. For x of 0, y of 0 equals 1, 1. The t-axis cannot be accurately labeled, but the x and y axes should show key values. So how can we do that? Well, so we know that x and y both start at 1, 1. And maybe actually instead of doing x first, I'll do y first, because that's a little bit easier to visualize. So here I have y over time. So what's y going to do over time? Well, first of all, y starts at a value of positive 1. So let me zoom out just a little bit here so we can see this a little bit more distinctly. So y starts off on this axis. That's my y-axis. starts off at positive 1. So the first thing I'll do is I'll come over here and I'll say, okay, y starts off at positive 1. Well, what does it do next? Well, we see that the orientation is in this direction, so the points are going to, this point, if we pressed play, would just circulate around this ellipse. And so what is y doing on this interval? Well, from here to about here, the y value decreases, right? So up until about here, y continues going down, and then from there, y starts to go back up again. So you have to visualize this in 2 dimensions. So from here down to this point, right about here somewhere, the y value is going down. The y component of that ordered pair circulating around here is going down. Now from here to about, where is it? From now y is going to be on the rise. If we continue to trace this point along here, this y value would increase until it hit about that location. And then from there, we see that from this point to this point, y is going to come back down. And that's just going to repeat over and over and over again. So where does y go? Let's think about this. So y starts off at 1 and then decreases down to just under -2. So we'll just call that about -2 1/4. So in this graph, I can plot, at some point in time, here's -1, -2, -2 1/4. I'll just put it right about there. Okay, so there's -2 1/4. And from there, that point starts to go back up until it rises to about positive 2 1/4. Again, I have no semblance of time here, so I'm just trying to eyeball this and say, okay, so about here we'll say it reaches 2 1/4. Now it's not going to be straight lines, right? These are smooth curves, so in all likelihood it's going to look something like this. Okay, and then once it reaches that third point, or it goes from here to here to here, now it's going to arrive back at its starting point, which this was an x value of 1. So next we expect this graph to decay back down to 1. I don't know, again, how long this is going to take, so I'll just draw it there. And again, kind of a smooth curve takes us back down. And you can see that this is going to be periodic because now the same thing is going to happen. Function is going to decrease back down to -2 1/4, come back up, and so on and so forth. It's not necessarily going to be a perfect sine or cosine function, but it will be periodic. Now x of t is pretty much doing the same thing, except x starts off by increasing. Remember, x is in the right-left direction. So let's clear off some of this. Actually, maybe I'll just use a different pen. Okay, so from this value, x is going to, the point moves along here, and x is increasing, x is increasing, x is increasing, x is increasing, until about this point, x increases. But then from here, as we start to move along the curve, you can see that if we're keeping track of the x-axis, that value is decreasing until it hits about here. So from there to there, the x value is decreasing. And then the x value continues increasing along here. X is getting bigger, x is getting bigger, x is getting bigger, x is getting bigger, x is getting bigger until it hits this point. So here x starts off at 1 and then moves to a point that's just slightly bigger than 3. Again, I'll just pin it right about 3.2 or so. So x is going to start at 1. X is going to start at 1. So there's 1. And then it's going to increase to about 3.25, we said. Next, after that point, x begins decreasing until it hits about this x value here, which is about, again, -3.25. And from there, it's just going to increase back to 3.25, decrease back to 3.25, and repeat that process ad nauseum. So here we're going to then eventually decrease to -3.25, then increase back up. And on our way up, we're going to pass our starting point again. So maybe it's going to look like this. If we just wanted to graph one period of this, it would look something like that. and then it would come back up to 3.25 and then go back down, and repeating this process indefinitely. So even though we couldn't solve this differential equation, the point is we could try to get a sense of what is happening to x and y over time. And this is really all we needed to do is generate a phase plane, and from there we could extrapolate. So if we were just interested in just understanding how x and y behave over time, this phase plane would do us a great deed. So we'll go ahead and stop here at this video. It's already getting really long. So this just introduces the concept of differential equations. In the next lesson, we're going to get into working with some of the linear algebra basics before we start really attacking some of these completely coupled systems.